So we are having a Codeforces contest today, the educational round 193. So I'm just attempting this and let's see what happens, whether I'm able to solve the problems or not. I'll just try. So before that, let me just do a bit of multi-type for type razor. Just feeling a bit bored, so possibly we can play one game. It's taking a bit time to find ways. Hopefully I'll get one. Yep, I got one. So on the gig, you will sound way to the audience if you are playing from. Yep, I hit 73, which is okay for now, not my best, I would say. I'm just warming up my fingers to start coding. So let's see what is the level of the problems. I mean, like, if I talk about the code forces educational rounds, I think the problems are not that much tough when compared to the normal rounds. So hopefully I'll get a bit easy problems and I'll be able to solve the problems. Talking about my rating, I am currently an expert rated on CF and my personal best is always 1800. And I think I have a potential of hitting a candidate master rating. But I mean, like, there is an up and downs in my rating graph. So hopefully I'll hit a decent rating after this contest or whatever it's going to happen. I'm ready for that. So we are ready. So the titles are okay. So the card give the red and cards. Okay, the values and okay. Whichever two cards wins. Okay. Okay, there is the card that wins against. Yeah, got it. So for the two, I think. So first of all, if the largest card is just prime, then it's just we just are going to win, or else I think we're gonna lose or what. Again, this is prime, but 3 2. So 3 2 means okay, n plus 1 should be prime, I think. That is the condition. So the condition is simple. We're gonna just do a prime check for n plus 1. I just look at the constraints. Okay, sum of n. So we just can run square root of n. We take the input. Just check whether it's prime. How do we check? Yes, see or no, I think. Well, I think it should be sure. I'm sure that it's gonna be this. We need to yes, run check. Just check with this input. So it's just running. So yeah, let's just submit this. I made the first submission, so have to give the contest now. Yeah, hopefully I get the acceptance. And we have got the acceptance. So just get the four problems. Just let me read the file. So a panel consists of n signal modules arranged in a row. Each mod contains okay. Okay. Okay, so he can swap at some instant. Yeah. Okay. Maximum number of modules the hypercarp can keep. Mhm. Mm. So we can just perform a swap once. So tricky, bit tricky. So let's just take the input first and think about the problem later. So I just took the input. Let's just run a few, I just dry run a few test cases to think what it's gonna happen. 1 2 1 3 1 2. So The first test case is pretty straightforward. Second test case we can keep everything. This is again one. We can also perform a swap at most once, so makes it a bit interesting. Yeah, B problem is a bit tough, I would say, personally. Like, looks like some sort of dynamic program, but again, it's a B problem, so I'm not expecting a complicated approach. Let's just read the statement D. So given n elements, doing testing that turned out that two adjacent modules of the same color may yeah, got it. So may remove any modules, okay, after that they shift, and there's a backup. In addition, there's a backup. He may, okay. So he cannot remove modules after the swap. So he has to remove the modules before the swap. No, he has to remove the modules and then apply the swap, right? Yep. So you can just apply a swap and just fix it out. So the trick here thing is remove and then apply swap. Hmm. So we can apply a swap later on, right? Hmm. Suppose there is a, so you can, I mean, like now if you just swap it out, yeah, you can always swap it out. Yep. So B, B, A, B, B. You cannot swap this. You cannot swap this. So in this case, you just stuck out, right? Hmm. So it's trickier in the sense like what I have to do. I'm thinking greedily. So the previous is now as an equal. I can just bear one equality. But obviously, once I just swap it out, we just don't care, and we can literally apply operations as other things, but we cannot touch that. So the thing is, I got the approach. So first, wherever the number of things is greater than two, we just remove it and just reduce it and got it. So first we simplify the problem. We can maintain a temporary vector. I think let me just think it a bit deeper in the sense that 1, 1, 2, 2, 3, 3, and there will be something like this. Then we can swap and fix one of them. So later, yeah, we can just try out whether that we are swapping this thing and what is the number of things it's solving. Yeah, and then we can just, yeah, got it. So the solution is pretty straightforward. So what I do is So start from the first index. Row. So just push back it, and then we just try out the swap. Initially, we have to remove these things so that is unavoidable. Now apply swap. So now we're swapping out a couple of things. It's going to be 10. So the reductions, I'm assuming the reduction is 0. So now we're swapping out a couple of things. So we maintain a del. What was the scenario in it? So we're swapping out this and this. If I not equal 0, and then temp of I is equal to temp of I minus 1, and that's plus plus. So the initial thing is plus plus, and I is less than 1, and then temp of I plus 1 is equals to temp of I. It's going to be not n, so it's capital N. I plus 2. So this, in this case, what we do? We net plus plus. And then swap, fin, fin, final, final. So you just again just take these two cases. What's happening right now? In this case, just increment the fact. So I mean, like now what we need to do is, so the final is less, and the main of ends, comma CP minus CP plus Fine. And that's what is going to be delta. Obviously, we minimize the answer. So let's check it out. I mean, test it with a few test cases. Uh, whether it works or not. 161 something. We're getting a bit. Let's read the compiler. Let me read out the code was wrong. Okay, here is a mistake. I think this out of bound access. So first is case getting 0. The second test case seems out to be interesting. Initially they were equal and currently now looks like a bit interesting. I'm getting a negative one. It seems out to be interesting. Okay, number of elements that are going to be present in the array. What is the solution? I'm just debugging and checking what's wrong with the approach. So if they are both unequal, yeah, I just need to reverse swap. That's wrong. I think that's where the mistake starts. 6. 161343674 345 B. I don't know whether I get acceptance. I should get, I think. The thing is pretty straightforward. So we're checking the conditions always by performing the operations. We're too late still with the acceptance. So you get matrix. Initially, all the elements are equal to 0. You're giving two arrays. Yeah. The elements in each array are strictly increasing. Choose a number C and a row for the matrix. Okay. We can pick any row. Okay, got it. Mhm. Mhm. Okay. It's not clear what to do, but it seems out to be a bit worst problem. So, okay, distinct elements that occur, right? And what about the thought process for this? It is about picking a few elements, right? So my intuition is you can either see, forget about n. You can pick n elements from array B and n minus 1 elements from array A. That is the case. Or you can pick n elements from n and minus 1 from B. This is the case. But you cannot never pick everything out. So now we'll try out optimally both the things. So an element might be occurring both in both of them. So let's look at this. Suppose this is the case, then you know it's 6. So if you look at this, then you know it's just like 4 plus 1 over this. So we just pick this 5 plus 4 and 9. So the intuition is straightforward. Let's create the 5. See, let's see. So possibly just take the n over the n in it, x1. So maintain set. If that element specifically is occurring in, yeah, then we avoid it. So our main goal is to pick it out, right? And then from that we just pick everything. So that is the optimality. Yeah. So in the sets, what we do? In the first set, we pick everything. Pick n from A and m minus 1 from B. So current need is m minus 1. So that's already present in the first thing. Yeah, it's gonna be B. Continue. So n e greater than equal to 0. Else e minus 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 n plus equal to b of I. So in that case, we have the first answer. So similarly, we just do pick N minus 1 from A and M from B. The same thing we just repeat. Copy this everything. Just change the variable names. So we just start from y minus 1. So I wrote up a greedy code that looks like intuitively it's correct, but there are a lot of mistakes in finite loops. So, hmm, hmm. I think I didn't dig. It's a big thing. Let's just take the input. First is I'm getting 12. Looks funny, but well, how 12? That is what is trick here. Yeah. So we're breaking, right? How? Okay. So count function is not working well or not? I don't know. Debug. Okay, let's just check. Okay. Check. Possibly answer 6. So, yep. What the fuck? What's going on? Interesting. What? Answer 6. Yeah, yeah, got it. I was just 6, 10. 10. Interesting. How 10? So we pick. So it's how it is 10. I don't know. I mean, like, how the word like or 10. That makes pretty much sense. 5 plus 3 is 8. It's going to be greater. Blender. 6915. Getting less in a few test keys. Just check it out. There are 4 rows. Now there are a few edge cases left out. Interesting how my codes are fading. So suppose I just apply operation. Okay, 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 okay. The approach is correct. Okay, we'll start. In the greedy process, the mistake I found. Okay, so how do I pick? So that is the thing. I'm just out of the box. Like this question is trickier, far more trickier than what I thought. Now I got a like conclusion that the approach is correct, but how do we pick the elements? How to pick optimally? So the greedy approach I got. So first thing is I need for me. We need to pick A elements and B elements from B such that all the elements are distinct and the sum has been maximized. So that is the trick. The approach is not really a game. I mean, like approach is thinking about. So we'll take that buffer, right? Hmm. Hmm. So I just fucked up, I think. Looks like I'm just overthinking. So yeah, I just changed the approach and got the acceptance, but it was a bit trickier in the sense like I was stuck for a lot of time. That's what deep wrong. So his ship is initially located at position this. He wants to reach X, Y. Okay. It's a bit tricky. I mean, like the sense, I'm not getting what to apply or what to do in this problem. So the thing is, we just gonna reach that point somehow. So I just am thinking with some greedy approaches. I'm having a few doubts in the question. Mm, well, the only thing that we need to minimize is the Euclidean distance. So we don't care about other things. So that is the trick. If x equals to y, we can always reach, I think. Hmm. So we can binary search for the moves. The thing is just binary search for the moves and then just try to go as much close as possible. $20 just looks like too much. But because the constraint, it's 100 is also there. So I got the solution. The thing is yeah, we are applying n moves. Suppose I assume we are applying n moves. So we need to try to apply I moves. And now how do I apply I moves? If let's write the brute force and I'll try to optimize. So capital X. If Yeah, the value to break out from the entire loop. So that makes sense. Print the str, I think. Let's see whether it's correct or not. I'm hitting a submit to see what happens with the problem D. Yeah, it's a time limit exceeded. So the proof is the more operations we are able to apply, we're getting more close. So a binary search basically, I just first wrote out the brute force and I just then thought, why can't you simply binary search for the solution? And this optimal strategy is pretty simple. Like we're taking this decision greedily to kind of get as much near as possible. So if we are able to apply more operations, means we're going to get closer. That is the approach. You can even increase the constraints. Yeah, I'll just try the E. So you get a tree with n vertices. The diameter of the tree is a simple path of maximum length in the tree. The length of the path is the finite. Uh, so basically, you get a tree of n vertices. Diameter of the tree is simple path of maximum length in the tree. The length of the path is the number of edges it contains. So E problem I didn't read actually. You call integer key. The intersection it contains exactly k edges. The constraint is a bit weird. I don't think I will be able to solve it in 15 minutes. I think I can stop here possibly for today. If I look at the number of submissions, it's just too less, I think. And if I just somehow fast solved ABCD, I would have been in a better position than this. Doesn't look good, this position for now. Yeah, key. But what can we more or less do? We can just focus on the things, right? I mean, like the D problem is really simple, and C was even simpler. But the thing with C was I just didn't read the question well. Like I missed out the constraints that it is less than n plus m. That's all. That made the problem's implementation really simple. Otherwise, we are just complicating things, whether it's there in both of them, this and that. So constraint reading the constraints is important in code forces, especially. Okay, let's now discuss the solutions of all the problems. I don't think I will be able to solve it. But let me just look at this question at least. Supposedly two diameters with having exactly k is common. So the diameter is has an odd length. So specifically mentioning that the diameter has an odd length. That is, I don't know why it's being mentioned that it's an odd length. So first find the diameter. I don't think I'll be able to solve it in 10 minutes. Let's just chill with whatever we have currently. I'm just looking at my college standings. Okay, so let's start with the explanation of all the problems. So the first problem is pretty straightforward. So you're given a few cards, and we need to determine whether okay. So the larger element wins. So if the one of them is dividing the other, then like there is no number that divides every number. So obviously the larger number has to win, and for the larger number to win, like then there should be no, it should not have any divisor except one. So it must be a prime number, and that's why we just do the prime check for the n plus one. And if it's then we print yes. So if there exists any number that wins against every other card, so that is the condition. So we just run up a primality check, simple primality check on n plus one, and just print yes or no based on that. Coming to the second question, what we have done here is, again, this question is just like there cannot be no two adjacent elements can be seams. That is a condition. You can remove a few elements and also apply a swap after removing the elements. So for this, my solution was, let me just explain out the code directly. So the thing here is, like, I go through all the elements, and I just make sure that there is only single repetition at most, because otherwise the swap doesn't make any sense if there are more, an element repeats more than two times, like it repeats three times, then the swap doesn't make any sense. So for that, I made sure that the element only repeats twice. So thrice doesn't make any sense. Then the swap operations would be just useless in terms like of reducing the cost. So, and we are compelled to remove the element when they are more than two, repeating more than two times or like thrice. And after that, after removing that, I just try to apply the swap in each and every possible swap, like brute forcing each and every possible swap, like with the remaining elements. And then I'm just calculating the increment in the answer, like how many removals I'm able to save with that. So that is pretty straightforward. I'm just applying a few conditions, initial matchings and the final matchings, and just adjusting out that and just printing out the n minus answer. So I just need to minimize the number of removals, right? So that is the brute force approach that I'm applying here, trying out each and every swap. So removing and then trying out swap, whether optimizes the solution. So this is what it is, and it should work for the problem B. Talking about the problem number, I think, yeah, problem number C. So this is a bit trickier question. So I hope you went through the problem. So you need to few observations here for the C problem. So these are the two optimal possibilities. Pick n elements from the first array and then m minus 1 elements from the second array. Similarly goes for the other 10. We consider both of them and try to pick. This is always we can constructively prove that we can always satisfy this. But now how do we pick such that the total sum of distinct elements is maximized? So that is what we need to keep in our mind. So we just go and just go through that, go through all the possible values, distinct values, like it should be greater than one. So and then if it's present in both of them, we can take from any one of them. And then we are also keeping a track of number of common elements that we have taken. If it's present in any one of them, then we check whether we can take it from it. If we can, we are taking. If we cannot take, then we are trying to reduce one of the common elements if possible, and then again take. So that is the greedy approach. And same goes for the other element, other present in the other array as well. And this other cases n minus 1 elements from A and m elements from B. Like n and m are the number of rows and columns as mentioned in the question. So just again the same approach I'm applying, no change in the code, and then maximizing the answer is to do like maximum of the both cases. So just print the answer. Talking about the fourth problem, this is the trickier problem. I don't know why it's loading. So let's just first understand the brute force approach that I implemented. The brute force approach is called TLE. Then I optimized this brute force approach. So for that I have taken the inputs, and then I'm fixing a few number of operations, that this is the number of operations, and I'm trying to construct with this whether it is possible or not. So the maximum number of operations that we can apply, so that more the number of operations, the more the closer we get to that point, right? And then we greedily try to get as much close as possible. So how do we get it? We are using the remaining distance in x and y. And if the remaining distance in x coordinate is greater, then we just reduce by I minus j. I minus j would be the contribution of the ith operation if we apply an x over it. Means it's just if you run a few test cases, then you will understand this condition. And else you just gonna just do this. So if it's just going out of bounds, then it doesn't make any sense. Else we just update the answer. And this is a brute force solution which will fail because of the constraints. Like if you look at this, it can go 20,000. So 20,000 times of 20,000 times of 100, which is 2 into 10 to the power 10, which is obviously a TLE. So let's go to the optimal solution. Like we know that here the observation is we can simply binary search for the answer. Why we can binary search for the answer? Let me just show. So here, if you just look at this, the only thing is we just binary searching for the answer. Everything is same, the same code. And just when it's going out of bound, we're trying to reduce the answer. Else we're just updating the string and looking for a greater answer, greater number of operations to even get more closer to the x comma y. And then finally printing out the answer. Initially it was an empty string, so that is going to solve. So I hope I have tried to explain the solutions to my fullest. and let's end this. Bye bye.